So now we're ready to turn our attention to an example program that illustrates how concurrent map collector can be used. And this is a really cool example. This example will create a couple of different subclasses of map that associate unique words in the complete works of William Shakespeare with the number of times each word appears. And this was certainly quite instructive for me when I played around with it. I never knew some of the things were about to be revealed in a minute. And more importantly than this example, which is just a fun example, it also shows the difference in runtime overhead between collecting results in a parallel stream versus a sequential stream and using concurrent and non-concurrent collectors for various types of Java map implementations, including HashMap and TreeMap. And that's the really cool part of this example. So what I'm going to do is I'm going to run the code here, and I'm going to show you the results, and then we're going to talk about the driver program and see what it all means, because it's really interesting to see the results first. And this will also teach you some interesting things you probably never knew about the complete works of William Shakespeare. So what we do, as you'll see when we look at the code, is we go through the works of Shakespeare. We first go through the first 1,000 words, then we go through the first 10,000 words, then we go through the first 100,000 words, and then we go through all the words in William Shakespeare, which, according to my reckoning, is about 910,000 words. And for each of these things, we're first going to put these words into a hash map, and we're going to use sequential streams and parallel streams, and we're going to use concurrent collectors and non-concurrent collectors. So that's what we're comparing against. And the key thing to note here is when the number of words is small, it doesn't matter. But when the number of words gets to be all the words in Shakespeare, then lo and behold, the concurrent hash map using parallel streams is by far the winner. And that's because it's collecting all the data into that one and only hash map from all the threads concurrently. In contrast, you can see that the parallel non-concurrent hash map performs pretty well, but it has to merge incremental hash maps together. And so merging obviously has a little bit more expense than synchronizing on a concurrent hash map. So it's still fast, but it's not as fast as using a concurrent collector. So that's point number one. And then point number two is that the sequential implementations are not anywhere near as good. And that's, of course, because I have a lot of cores. I have 8 cores on my computer. So we're not quite getting linear speed up, but it's doing pretty darn well. Then when we get to the tree map test, you'll notice once again that when you have a small number of words, doesn't make a lot of difference. But when we get to the total words in Shakespeare, a couple of things are notable. Number one, for tree map, concurrent tree map, which is concurrent hash map for everything up to the very final finisher where we turn it into a tree map, that's the fastest when used with a parallel stream. And again, it's substantially faster than the parallel non-concurrent tree map. And what you're really seeing here, notice the difference in performance between the concurrent tree map and the non-concurrent tree map versus the hash map. So first of all, you notice that hash map is just always faster, and that's because hashing is faster than putting things into trees. So that would be sort of one obvious conclusion. And number two, notice how much more expensive merging is with tree map versus merging with hash map. So you'll see over here that merging with hash map is pretty fast relative to the concurrent hash map, which is not merging. But when you take a look at tree map, it's substantially faster to use the concurrent tree map than to use the non-concurrent tree map. So that's because merging overhead is costing you more for tree map, which makes sense. Maintaining a balanced binary tree is going to be more computationally expensive than maintaining a hash table. So, and merging into hash tables. So that's the first point. Notice the difference in these things. And then also notice how the results, well, also just notice the results. So these are the final results. There's 23,518 unique words in Shakespeare out of a total of 910,000 words. So there's a lot fewer words than there are, a lot fewer unique words than there are words, which is probably no surprise. And then we can also find out the top words. So these are the top words. I guess no surprise, the would be very popular, or a. most of the most popular words are kind of boring, and you don't see interesting Shakespearean style words till you get a little further down. So here's a good Shakespearean word, thou. And another Shakespearean word is thy. See, thy. And somewhere we have like shall and thee and lord and king and sir. So that's just basically the words that are ordered by key. I'm sorry, ordered by value, not ordered by key. So we print the results out a couple of different ways. So that's a quick overview of the performance of the different variants of these collectors, both parallel and sequential streams, both concurrent and non-concurrent collectors. And the take-home point here is that for this particular application, where merging is fairly expensive because we're using strings, as we'll see, it's a win to use the concurrent hash map as the mutable result container for a concurrent collector, and then convert that at the very, very, very end in the finisher to the tree map. So if you want to have an ordered map at the end of all this stuff, then this is a very, very nice way to go.